We are going to continue our conversation about linear and rotational motion, but now we're going to focus more on example problems. Recall our kinematic equations for rotational motion. We have alpha is equal to omega final minus omega naught, all divided by time, where alpha is the angular acceleration, omega is the angular velocity. We also had change in angle is equal to the initial angular velocity times time plus 1/2 the angular acceleration times time squared. The third one was not a vector equation and dealt with omega f squared equaling omega naught squared plus 2 times alpha delta theta, and just gave us the magnitudes of the quantities involved. These, along with our linear equations and how to connect the two, provide a large amount of information which we can now use to solve several problems. Example 1. A pulley is attached to an electric motor. If that pulley has a radius of 30 centimeters and is initially moving with an angular velocity of 5 radians per second, and 2.5 seconds later it's moving with an angular velocity of 8 radians per second, we want to find out what's the angular acceleration of the pulley during this time period, how many radians did the pulley spin through during this time, and how many revolutions were completed as it spun for the 2.5 seconds. As usual, we should write down what we know first. We know that the radius is equal to 0.30 meters. The initial rotation is omega naught, and that is equal to 5.0 radians per second. Now, using the right-hand rule with the image drawn, I know that omega is pointing out of the page, or screen in this case. Omega f is 8.0 rads per second, which is also pointing out of the page. And we know that 2.5 seconds has elapsed. So the first question is asking us to find the angular acceleration, alpha. To do this, I will use that first kinematic equation. We have omega f minus omega naught, all divided by time. So plugging in our numbers, we have 8 radians per second minus 5 radians per second, all divided by 2.5 seconds, which gives us an alpha of 1.2 rads per second squared. And this is a positive number, so we are going to say it is pointing out of the page. Part B is asking us to find the angle that it spun through during this time. That means we're looking for delta theta. So I'm going to use the second equation. Since we know all the variables in this, we can just go ahead and plug them in and find out. So we have 5.0 in the positive direction times 2.5 seconds plus 1/2 1.2 radians per second squared, also in the positive direction, times our time squared. All of which, when we plug it in, we get 16.2 radians. The last portion is asking us to find out how many revolutions this is. So if we need to find the number of revolutions, which I guess technically is rotations in this case, we need to remember how many radians are in single rotation. So we have our delta theta, and that's going to be times 1 rotation divided by 2 pi radians, because 2 pi radians is once around a circle. So 16.2 rads, multiply that by 1 rotation over 2 pi rads, and we get how many times this spun around, which is 2.6 rotations in the end. You will notice that algebraically, these problems are very similar to the ones we did in the first unit of linear motion. Kinematic equations for straight motion and kinematic equations for angular motion are very similar algebraically. Example number 2. An old-timey bike with a wheel with a diameter 1.2 meters spins at a rate of 4 radians per second. Here we're talking about the larger of the two wheels. So part A, what is the tangential speed of a particle on the edge of the tire? Part B, what is the tangential speed of a particle halfway around the edge of the tire? Maybe they put some baseball cards in the spokes or something. And finally, how fast is this bike moving? To find the tangential speed, we need to remember how to connect linear motion to rotational motion. So V at any given time is going to be equal to R times omega. In this case, R is going to be 0.6 meters, half the diameter. So 0.60 meters times 4.0 radians per second. And we get a tangential speed on the edge of the bike of 2.4 meters per second. A similar process will be done to figure out the tangential speed of something halfway to the edge of the bike. So V tangential in this case is going to be our new R times the same omega because the bike tire moves as one. So we now have 0.30 meters times 4.0 rads per second. And this gives us a whopping 1.2 meters per second. To answer the third part, how fast is the bike moving, we have to consider what's actually propelling it. Now, for a bike like this, the speed is going to be equal to the tangential speed of the wheel where it is in contact with the ground. So for this, we can say that the total speed of the bike is going to be equal to the tangential speed of the edge of the larger tire. Or the bike is moving at 2.4 meters per second. What is different for the little tire? It has the same tangential speed, or it would be left behind. So it has to have a different omega. So it'll have a higher omega because the radius is smaller in order to maintain the same tangential speed. This is an essential thing to consider when designing gears, as the different radii allow you to change the rotation rate of different mechanical pieces. Example number 3. Here a 2,000 kilogram car rounds a flat curve of radius of 60 meters. But the car has a velocity of 9 meters per second. Note that this is a relatively slow turn and it's not a banked curve that you would see on a faster highway. Question A. What is the centripetal force acting on the car? And what is the cause of this force and its resulting acceleration? To solve part A, we need to remember our formula for centripetal acceleration. So we know from Newton's second law that F net is equal to mass times acceleration. So we do a substitution. We have mass times v squared over r. So here we have 2,000 kilograms times 9.0 meters per second squared all over 60 meters, giving us a force which is 2.7 times 10 to the third newtons. Now this is the net force, but in this case it is also the centripetal force, which is causing the car to turn in a circle. Which leads us to part B. What is causing this? If we draw a force diagram for the car, we know that there's a weight force straight down, a normal force from the road pointing straight up because it's a flat curve, which means the only force that could cause this to turn is actually a friction force. Could we use this information to figure out the coefficient of friction between the tires and the road? Of course we could. We know friction is going to be equal to mu times n, which is the same as mu times mass times gravity in this case. Given the numbers we have, we could plug it in and figure out that the coefficient of friction for this example is 0.14. So it's a very wide turn with not a lot of friction, but they are going relatively slow for a car. Where this gets interesting is if we have a banked curve. So you've seen this on the road where the roadway is actually angled depending on how fast the traffic is at some sort of elevated angle. Here our force diagram is going to look a little bit different. If, for example, we're driving at the exact speed that the curve was designed for, we can actually balance out the weight force downward with a normal force off at an angle with no friction, because the perpendicular and parallel components of the normal force will account for our net force. So we can have a centripetal force simply by the normal force. But that is the ideal position. Now, that's not always going to be the case with traffic. Sometimes you will have a friction force that's preventing you from sliding up the ramp because you took it too fast. So that'll contribute to your centripetal acceleration. But if you were going too slow and you would slide down the ramp, you would also have a potential friction force in the opposite direction, which would decrease the centripetal acceleration. So this is a very complicated problem, and you would need the specifics of the speed and the angles to solve. But conceptually, you can see how everything works out in the end. Example number 4. A 500-gram ball is attached to a string that is rated to have a maximum tension of 8.0 newtons. This means anything greater than 8 newtons and it will snap. The ball is tied to 1 meter of string and is whirled overhead in a horizontal circle. Part A is asking us what is the maximum speed that the ball can have before the string snaps? And what is that maximum angular velocity of the ball? Well, since we're given the maximum force, let's start there. We know that 8 newtons is our max, so anything greater than that and we'll snap the string. This is going to be equal to our centripetal force, which is mass times our centripetal acceleration. So we plug in v squared over r for the centripetal acceleration. A little bit of algebra later, we know that this tangential acceleration is going to be equal to the centripetal force times the radius divided by the mass of the ball, and everything is square rooted. We can plug some numbers in here. For the maximum, we have 8 newtons times 1.0 meters, all divided by 0.500 kilograms to the 1/2 power. All right, so plugging in our numbers, we get 4.0 meters per second for the tangential velocity. Anything faster than that, and the centripetal force would be greater than 8 newtons, and the string would snap. Now for part B, we have to find what the angular speed is at that point. Recall that the connection between tangential speed and angular speed is a factor of r, which would mean that omega is equal to the tangential speed divided by the radius. In this case, we have 4 meters per second divided by 1.0 meters, leaving us with 4.01 per second. We have to recall that this is actually 4.0 radians per second. One other thing we should discuss about a situation like this is if we take a bird's eye view, we see that the ball is swinging around in a circle with the omega. So if we do the right-hand rule, it's pointing out of the page. At that moment, the tangential velocity is off in this direction. A good conceptual question would ask, what direction would the ball move if the string were to snap at that instant? So if we cut the string right then, is the ball going to continue moving in a circle, move in a straight line, move perpendicular? Remember, the force is inward, but once you snap the string, the force is not existing anymore. So the inertia that the ball has in that direction means that it will continue moving in this direction, at least in this plane. Now, the guy up here swinging the ball means there will also be a parabolic motion, and it will fall down if you want to consider the z direction. Just remember that inertia, Newton's first law, still applies. Once you remove the centripetal force, you no longer have a rotation. and that's because the force was causing the rotation. When we talk about rotational momentum later on, keep in mind there is a difference between something spinning about itself and something being spun because of an external force, in this case the tension on the string.